Welcome to solverfy, the place where learning becomes simple. If you're struggling with homework, assignment, or doubt in subjects, don't worry, you are in the right place.
Hello and welcome to Engineering Mechanics, Statistics and Dynamics, Chapter 11, Problem number 8. So in this question, we're given a figure here that I've redrawn for us, and it asks us, basically given all this information with a horizontal bar at some sort of angle theta, as well as a spring, and it asks us what force P at the over down here will we have to exert on this bar to keep it at equilibrium position theta here. The big thing is that we also are neglecting the weight of the bar. So it's really just a bunch of balancing equations, balancing our triangles here, our right triangles that we're going to have to get into. So first things first, anytime we have a sort of setup like here that gives us a vague diagram, what we need to do is write our force diagram that can help us identify what forces are going to be, what forces that we're going to be looking at. So we have a couple here. We have the force down P. I've also redrawn some of these straight lines and given some things arbitrary names. The length I have of the spring is length S. We have the distance from the top of the bar here at point A down to where we'll be exerting our force P is labeled as Y. Also, when you write these out by the property, I think it's vertical angles. I don't remember the geometric property. The angle theta that A makes with the horizontal on B here is the same angle theta that we'll see down here as well. And that's pretty much everything that we're going to be looking at, that and the force from the spring. So let's just get into solving this equation. So first thing we're going to do is write down a couple things. We're going to write looking at our triangle here, right, we have a right angle between our force, our spring, Fs, and the bar itself, so we have a right triangle here. So we're going to use, our trigonometry here to give S this length here and the length of the spring. And this is the length of the spring when it's stretched. That's an important aspect, but we'll get back to that. Length S is going to be equal to A. Remember, going back up here, I got to go back up a little bit. This between these 2 points is length A. So that's going to be A times the sine of the angle here, theta. And then we're also going to take the differential of this for the virtual work aspect later in this problem. So ds is equal to A cosine theta d theta. If it's sine, there's no negative, and we just go normal positive cosine. We're actually going to give y the same treatment here. This arbitrary value y is going to be labeled L. Remember that L is the length of the bar, not L naught, which is the length of the unstretched spring. I know it's a little difficult, but this length of the bar here is length L. So y, that value there, is going to be L times the sine of this angle again down here. And same thing, we're going to take the differential. We have dy is equal to L times the cosine of that theta, d theta. All right, so now we have a little bit more concrete values for these S and this Y here. And so what we're going to do next is calculate the force that the spring is exerting on the bar itself. So obviously it's going to be K, that spring constant, times X, and that's the X. This X here is important to think about because it's the length of the either further contraction or the expansion of the string. So this X here is going to be that S. Here, I'm going to go back up here. Remember that this S is the length of the stretched spring. So we're going to take this S that we calculated, and then we're going to subtract that from the unstretched length of the spring, L naught, right? And that'll give us the total amount of distance that the string has stretched, excuse me. So again, we have an equation for S, which is A sine theta. So we can just write that in. So we have K times that A sine theta minus L naught. That's our unstretched. So we have total length stretched minus our unstretched. From here, we can just jump right into our virtual work problem here. So we have du is equal to 0. And that's going to be equal to the force, downward force, cross that dy here, right? The length in the same direction as our force here, y and P. But in this case, obviously, it's a differential dy. Oh, excuse me. We have du is equal to 0, which is that P cross dy, plus the quantity, in this case, it's negative Fs, our spring force, cross ds, because that's going to be our differential length of the spring. We have F and S over here. And the good news is that we have numbers for all of these aside from the green P. We can pretty much just plug these numbers in and do the algebra that we need to get this problem solved. So we have plugging some of our numbers in. Again, we have 0 is equal to the quantity P cross our dy. It's going to be L cosine theta d theta. If we go back up just last time, dy L cosine theta d theta. And we're going to do the same thing with ds for the second part here. So we're going to plug in our values for fs and for ds as well. So we're just k times a sine theta minus L naught that we calculated up top here. And the same thing for our ds. Sorry, wasn't looking up. So next up, we're going to just do our cross products that we can. So since these guys are just going to combine nice and easy, since they're in the same direction and everything. So we're just going to have P times L cosine theta d theta minus, because remember that negative force, spring force is up top here. We carry that over down here as well. Minus K times A cosine theta d theta times that A sine theta minus L naught. So once we're finished with this, it's just a matter of getting our like terms out and putting everything in terms of P. So I'm going to take out a cosine theta d theta. You can see there in black from both terms here. So we can just kind of get rid of those since we just have 0. And I'm also going to move the second term in our equation here to the 0. So we just have it all in the same area. So what that's going to look like is they're going to have Ka times this other rest in blue times A sine theta minus L naught is equal to just simply P times L, since these terms in black here went away. And then we just divide by L to get a full equation for P. So our final answer for P is going to be equal to Ka times the quantity of A sine theta minus L naught divided by L.